My name is Stefan Sommer. I'm a mostly retired professor in the Department of Biological Sciences at Northern Arizona University, and I'm also on the board of the Northern Arizona Climate Change Alliance. Today, we are going to be talking about climate refugees and Arizona's future. We're going to talk about a rich complexity of different things that relates to why people become refugees and how climate change is impacting that. The issue of refugees is a whole complex suite of different pressures that people feel because for one reason or another, they can no longer make a livelihood where they had been living and in the way in which they had been making a living. And many of those kinds of pressures on people are now being exacerbated globally by climate change, to where we have tens of millions of folks every year being displaced by climate disasters of one sort or another. So as we get into this complexity of different things, I'm going to briefly go over some of the climate change basics again. And for those of you who were with us last week, I'm sorry that some of it will be a repeat, but I'll try to go through that quickly so that we can get to the climate refugees aspect of it.
Stefan, we have a question. Will you be addressing the meat industry impact?
That's an excellent question, of course, and we did a little bit last week, and we will more as we get into next week's presentation, which will be about building a path forward. So just to start out with, even in the United States, we have been feeling the impacts of climate change in larger and larger dollar amounts. In the United States, oftentimes we measure impacts through their dollar effects. But of course, globally, many people are dealing with human impacts from a human suffering perspective. And so just to start here, in 2017, we had 3 hurricanes in the United States and wildfires. And these various kinds of things that have been exacerbated by climate change cost the United States over $306 billion. So the impacts in terms of dollar amounts are becoming very real. One way to look at that too is in terms of the projected effect of climate change on gross domestic product for different countries around the world. And this was a Scientific American recap of a study in which it projected that if we meet the terms of the Paris Agreement on climate change, that the impact on gross domestic product will be less. All that is in the green. If we do meet the Paris Accord requirements, then it'll still have a negative effect on GDP. But if we don't meet the Paris Accord, then those effects will become much more extreme. And you can see that generally speaking, for most countries, the hot countries, the cold countries, the poor countries, the rich countries, and overall for the whole world, climate change is projected to have more and more negative effect on gross domestic product. For the United States, certainly it does. For China, if you take a look at that, why China looks like if we do meet the Paris Climate Accord, it gets a bump up in its gross domestic product for a time period. And if you look at Russia, it gets a pretty steady increase. And think for a minute, why would that be? For China, China is well positioned to supply wind and solar power because they're heavily invested into the production of photovoltaic panels and other related technologies. So if we do convert the way Paris Agreement calls for, then there's going to be a boost in their economy because they're positioned to supply non-fossil fuel-based energy technologies. For countries like Russia, and Canada isn't on this particular one, but it sees the same thing, for the higher latitudes, as things get warm, their agricultural productivity is actually projected to increase. Whereas in the United States and further south, lower latitude countries, I should say, things are expected to get hotter and drier. And so agricultural productivity is supposed to decline. So Russia and Canada will benefit from those shifts to agricultural productivity. Okay, just real quick, the climate change basics. Climate change is happening now. It's not some theoretical future. It's been going on for some time already. We've known about the greenhouse effect since 1824. CO2 and the Earth's temperature are strongly correlated, and current climate change is caused by us. So I'm just going to review the evidence for those things real quickly. Y'all know basically how the greenhouse effect works, but I'll just review it. So we get a lot of different sunlight energy, comes in all sorts of different wavelengths, comes to the atmosphere. Some of it's absorbed or blocked or refracted or reflected from the atmosphere, but much of it reaches the Earth's surface. And when it is absorbed by physical objects on the Earth's surface, it warms them up. Warm objects re-radiate towards colder objects, and many of those wavelengths are shifted towards the infrared, slightly longer wavelengths, thermal radiation. And so that thermal radiation is coming back up from the Earth's surface from all these warmed up objects. And it's that infrared thermal radiation that's absorbed by greenhouse gases like CO2 and methane and nitrous oxide and others. And so basically by adding more CO2 and other greenhouse gases to the atmosphere, we're thickening that insulating blanket that keeps the heat from escaping back towards outer space. And as we do that, we're changing the heat balance of the entire globe. And that's really what climate change is all about.
Stefan, this is Bob.
Yeah.
Another question from Zuba. Does climate change exacerbate natural disasters? If so, how?
So yeah, that's a good question, and we will get to it in just a second.
Okay.
So what I've just mentioned is basically we are adding heat energy to the atmosphere and to the oceans, and that heat energy is really what drives climate and weather. So we expect more extremes in a nutshell, but we'll get to that in just a second. So one way to look at the relationship between CO2 and temperature is to not just look at the Earth, but to look at our nearest neighbors, Venus and Mars. If you can see here, the Earth has what we call one atmosphere of pressure at ocean level, at the surface of the Earth, because there's one atmosphere pressing down on the gases that are near the Earth's surface. Mars has a relatively thin atmosphere, only 0.007 as dense as ours. And Venus has a very dense atmosphere, 90 times as dense as that of the Earth. Our greenhouse effect, so the temperature, if we had no greenhouse effect on Earth, the Earth's average temperature would be about minus 18 degrees centigrade. And life as we know it on Earth would not really be possible because most water would be frozen most of the time. As the result of only having 0.03% of our atmosphere being CO2, that's enough to give us a plus 33 degrees rise in what our temperature would be without the greenhouse effect, meaning that we have an average temperature of 15 degrees. So 33 degrees higher than it would be without that greenhouse effect. For Venus, which has a high percentage of CO2 in the atmosphere and a very dense atmosphere, their greenhouse effect is plus 523 degrees centigrade. For Mars, it has a high proportion of CO2 in its atmosphere, but because the atmosphere is so thin, it only has a plus 10 centigrade degree greenhouse effect. Okay, so just by comparing our own situation with those of our neighbors, we can see how strong that greenhouse effect can be. In our case, it brings us from unlivable conditions into livable conditions, and it's really a good thing overall. The only problem is that now we're thickening that greenhouse gas concentration in our atmosphere, so thickening the insulating blanket, and we're trapping more heat energy in the atmosphere and in the oceans as a result. If we look at the Vostok ice record, this is, if you look here, this is present, where it says 0, and it goes back 160,000 years. From the ice, we can look at the CO2 concentration in little bubbles that are trapped in that ice from the time when it was frozen, to look at the atmospheric composition of CO2, and we can see that it changes over time. And I want you to notice that here at the high point, 130,000 years ago or so, we were just over 280 parts per million. But we can also look at the ratio of heavy water to cold water, because it's a measure of the relative temperature of the ocean surface at the time that that water evaporated. So you can see in a general sense that when CO2 goes up, temperature goes up. As CO2 concentrations decline again, temperatures decline. And then when CO2 goes back up, temperatures come back up. So there's a general relationship over this 160,000 years between CO2 concentration in the atmosphere and the Earth's average temperature. So that's another way to look at it. There are many, many ways that scientists have looked at this, and there's really no doubt within the scientific community about the relationship between CO2 and the Earth's temperature. I'm just giving you just a few of the key pieces of evidence. So as of today, the concentration of CO2 in our atmosphere is at 417 parts per million, whereas prior to the Industrial Revolution, pre-1880, it was around 280 parts per million. So we've dramatically shifted the concentration of CO2 in our atmosphere since we started burning fossil fuels in such a big way. This record is from the top of Mauna Loa. It gives you an idea of the magnitude of increase. If you look at this from here, back in 1960, we were under 320 parts per million. And since that time alone, we've raised it by this much.
Stefan, I have a couple of questions.
417 parts per million. Yes, Bob.
Laura says, why was the CO2 so high 120,000 years ago? I have a similar question. I said, so the CO2 and the temperature change wildly over time. The Earth doesn't seem to care. It keeps chugging along. So is climate change really about humans rather than the Earth?
It's another excellent question. If you notice, though, and that's why I wanted to point out that even at the high point across that last 160,000 years, the high point was about 280 parts per million. That's what we were prior to the Industrial Revolution. So yes, there are natural variations, and that was during a particular geological period. And there are lots of different things that in the natural world also affect CO2 concentration and the Earth's average temperature. I'm not sure exactly what was going on 120,000 years ago, but we're going to cover all of those natural, what are called natural forcing factors that do change the Earth's average temperature over time. We'll cover it in some excruciating detail in just a moment. But meanwhile, let's focus on this record right here. If you look at this, this is a huge change. Anybody have any idea what this little red squiggle might be? So some of you probably know the answer. It's the annual cycle in CO2 concentration. And if you think about that, in the summer, the spring and the summer, when plants are starting to grow, photosynthesis is ramping up, photosynthesis takes CO2 out of the atmosphere as a raw material, combines it with sunlight energy to produce chemical energy like carbohydrates. Then when we consume those carbohydrates and burn them physiologically, we are taking in oxygen and we're releasing CO2. So respiration puts CO2 back out in the atmosphere. Photosynthesis takes CO2 out of the atmosphere. And so this red squiggle is basically the annual cycle between summer and winter. In the summer, there's relatively more photosynthesis and relatively less respiration, and so CO2 is being taken out of the atmosphere. And in the winter, there's relatively more respiration and less photosynthesis, so CO2 is being put back into the atmosphere. But if you think about this, this is from the top of Mauna Loa, this is where these measurements were taken. This order of magnitude for the red oscillation, that's the entire change in the net value of photosynthesis and respiration for all living things in the Northern Hemisphere. So for me as a biologist, that change, that amplitude of that red squiggle is a huge change in CO2. And yet it is dwarfed by this amount of change that is caused by human activities. Okay, so that, for me as a biologist, that puts it into perspective. The amount of change that we have made in CO2 concentration is huge compared to all the living systems and their effect on CO2. Okay, this is what I was telling you about. So all of these different graphs, I get this from my geology colleagues here at NAU. These various graphs cover the period from present to over the last 300 million years. And so these are representing what are called natural forcing factors that affect the Earth's temperature. And if you can see in this first graph on the very left, 0 again is present, and in this case, it goes back 300 million years. And you can see that across that 300 million years, the Earth's temperature changed dramatically across about a 10-degree centigrade scale. And the reason for that particular change across time is because of the tectonic shifts and the placement of the continents, which affected ocean circulation, which affects the way in which that heat that's coming in is trapped and captured on Earth. Okay, so because the continents were shifting across that 300 million years, it changed the way in which we trap heat, which changed the Earth's average temperature.
Bob Rothrock has a question, Stefan.
Yes, Bob.
Why is the current warming not just a strong natural cycle? And he says, I may see Uncle Bob this weekend.
Very good. Well, and we're getting to that. So thank you. Yeah, so what I'm showing you here is all of the natural forcing factors. And we'll use this as a basis to see how current changes are outside of the range of these past changes. Okay, so across the last 300 million years, the Earth's temperature has changed by about 10 degrees centigrade across a very long period of time. So the good thing about that is that biological systems had a chance to adapt from colder to warmer and then back to colder temperatures again. That adaptation takes time, but across 300 million years, the plants and animals can adjust. Now, if we expand out of that 300 million years here, if we expand out the last 3 million years of that, expand it out like this, now we're going from present to 3 million years ago across a 6-degree centigrade scale of variation. You can see some much more regular variations of increasing and decreasing Earth average temperature. And all of those are orbital changes. The change in the eccentricity of the Earth's orbit around the sun, the change in the tilt of the Earth's axis, and a variety of things like that. All combined, those different natural cycles are referred to as Milankovitch cycles. And here's how they affect the Earth's average temperature, have affected it across the last 3 million years. If we expand out just the last 50,000 years of those 3 million years, what we see is that about 12 to 14,000 years ago, we came out of a relatively cool period into a relatively warm period. And for those of you who know your geological history, basically that was when we came out of the last ice age. And the ice ages were driven by these orbital changes, which we know as the Milankovitch cycles. So we came out of the last cold period 12 to 14,000 years ago, the end of the last ice age. And again, this is across about a 6-degree centigrade range of temperature variation. And so we're in a relatively warm period already. If we expand out just the last 1,000 years here, then just across a 1-degree centigrade range of variation, we can see that there's still some variation in the Earth's average temperature. And those are due to various things that we can refer to as historical factors. Things like major volcanic eruptions can affect the Earth's average temperature, but these are, again, across a much smaller range of variation. So we've got all these natural forcing factors, the shift in the tectonic plates, all the different orbital changes, the way we orbit the sun, and then smaller historical factors like volcanoes. And in the short term, volcanoes can put aerosols and ash into the atmosphere, which blocks incoming sunlight, so they can have a cooling effect. But also they put more greenhouse gases into the atmosphere, so over the longer term, those volcanic eruptions actually have a warming effect. So again, it depends on the time scale. But in any case, these are all things that we can refer to as natural forcing factors. Okay, so, and here's really the smoking gun. There's lots of different evidence that goes into the conclusion that humans are the cause of current climate change, but here's the smoking gun. And it was first conducted by the Intergovernmental Panel on Climate Change in 1992, at which time they concluded that humans were the cause of current climate change. And since that time, there really has not been a question about that within the scientific community. There only has been a question about that within political communities. So in both of these graphs, you can see that the black line is the actual temperature record. And in the top graph, the red lines represent the best model that scientists could put together to look at all the ways in which the natural forcing factors, as well as the human-caused, or what we call anthropogenic forcing factors, affect the Earth's average temperature. And we do it by not just greenhouse gases, but also changing the reflectivity of the Earth's surface and some smaller effects along those lines. And you can see that the model really tracked reality pretty closely. All these red lines pretty much follow the trajectory of what we actually know to have taken place from the year 1900 up to, this was about 2005. And so they conclude on that basis, that's one way to test a model. Yes, this is a good model. This model really does track what's going on in nature with Earth's average temperature. And then once they were confident in the model, they then ran the model again, but they took all of the human forcing factors, greenhouse gases, change in reflectivity or albedo, out of the model. And then what the model did was this, in the blue lines down here. And basically, since about 1960, it's no longer tracking what's going on with the Earth's temperature. Instead, it's saying that with just the natural forcing factors alone, here's what the Earth's temperature should be doing. It should be holding steady or maybe even slightly declining across this time period from 1960 up through 2005. So this really is the smoking gun that says, no, it's not any of the natural forcing factors that are causing current climate change. It's human forcing, period. Everybody with me on that? And of course, here's the actual temperature record shown in another way. In this case, each loop around the circle is a year. You can see the months around the outside. And you can see two things. From 1850 through 2016, Earth's temperature keeps rising. And the other thing you can see is that the rate of rise has been increasing. Okay, so those are both really important points. So in a nutshell, what have we been doing to climate? Well, we've been adding heat energy to the atmosphere and the oceans. And what do we expect as a result of that? Well, we expect more extremes. When we first were talking about this back in the 1950s and 60s, the scientific community said global warming. They called it all global warming because the Earth's average temperature is increasing. There's no question about that. But when we'd have a cold snap, people would say, what are you talking about global warming? And so we realized, okay, we really need to call it climate change, because it's not that we don't expect cold periods and cold snaps. It's just that we expect the average temperature to keep increasing. But as we put more energy into the atmosphere and the oceans, we expect more extremes, because that power can be used to cause longer droughts, to cause stronger storms, to cause heavier flooding, all of those extremes, because we've put more energy into our climate system. And I don't know if y'all have seen this particular picture of the Earth before, but I love it. And I don't put it upside down for any political reason. I just put it this direction, this orientation, so y'all can see Old Man Wind. And here he is. There's one eye, there's another eye, there's his nose, there's a wisp of hair, there's his howling beard. So Old Man Wind, we're giving Old Man Wind that much more energy to howl up a storm. And we expect more extremes. So if you don't remember any of the numbers, remember Old Man Wind. Of course, we are seeing, as a result of Earth's average temperature rising and more energy in our climate system, we're seeing more frequent and stronger storms, more frequent and stronger floods, and more frequent and stronger droughts, as shown in this particular graph here. And it's not just the biologists and the scientific community that's paying attention to these things. It's also the insurance industry. This is from the International Insurance Information Institute. And they've been tracking since 1980. They've been tracking the number of natural catastrophes, because from an insurance perspective, that's really important for them. They need to have that information to build their actuarial tables in such a way that their income is covering their output. And if you can see the red at the bottom down here, those are all geophysical events like earthquakes and tsunamis and volcanic activity. And those have held pretty steady across time, and they're relatively smaller in frequency and intensity. If you look at the green here are tropical storms, hurricanes, that sort of thing. The blue are floods and mass movement like landslides as a result of saturation with water. And then climatological events, extreme temperature, drought, and forest fire are in the orange up here. And so you can see across this time period that these natural disasters have been increasing. And this is not science data, this is from the insurance industry. And the cost, also as plotted by the insurance industry, overall losses have been increasing, insured losses have been increasing, overall losses have been increasing pretty dramatically. And of course, that affects the way that they have to calculate all their actuarial tables. And one of the first businesses that really took climate change into account was the agricultural insurance industry in the 1970s already. They changed all their actuarial tables because they knew that more climate disasters were going to affect agricultural productivity, and they had to change their tables. So it's not that the business community was naive about this. They were actually tuned in, and here's some of the evidence for that. Okay, so.
There's a couple questions up here. There's a couple questions.
Yeah, okay.
Zuba asked the question, how does CO2 give the ocean more energy?
Thank you, Zuma. So basically, we're trapping more heat energy because of the greenhouse gases. That heat energy is not just in the atmosphere, it's also being absorbed by the land surface and by the oceans. So again, heat energy in the ocean also changes its circulation pattern and the way in which It generates tropical storms and hurricanes.
Laura?
So we're giving the oceans more heat energy in the same way that we're giving the atmosphere more heat energy.
Stefan, Laura has a question. So forest fires seem to be staying the same, but I thought fires have increased in a major way.
They have. Let's go back and take a look at that. In terms of these climatological events, if you look at this data, from a kind of data analysis perspective, those fires have been increasing. It's just that the relative cost of them has been much less than that for the tornadoes and hurricanes and some of these other things. So it's not that they haven't been increasing. It's just that relative to those other costs, they're not that increase doesn't show up as visible. So all these various extremes that we're seeing are affecting people's livelihoods around the globe and translating into more and more people being displaced by natural disasters. The International Displacement Monitoring Center, based in Norway, has been keeping track of these sorts of numbers. And in this map, they've got orange dots for people displacements caused by conflict and blue dots for those caused by natural disasters. And so you can see that this is in 2017 across 143 nations, 30.6 million people were displaced by conflict and natural disasters, which does include some of the geophysical stuff. I'd like to point out though here, they take all of the Syrian displacement, refugees, and put that under conflict. We're going to talk about that a little bit more detail further on, because really that conflict was started by climate change. There's really no doubt about that either. So we'll talk about that in some detail. So some of these conflict numbers really underlyingly are also climate disaster related. Here's the breakdown. This is again from 2017. All the orange is conflict, all the blue is disaster. And of those 30.6 million people displaced in 2017, 18.8 million were caused by disasters of one sort or another. These up here are the geophysical disasters. The rest of them, the 18 million here, are all climate-related displacements. So really, these are climate disasters are the overwhelming cause of people being displaced. In the United States, back in 2017, we had 3 different hurricanes. These show you the pathways of those and how they affected people. So many people were displaced by Hurricane Harvey, Hurricane Irma, and Maria, which particularly hit Puerto Rico really hard. And you can see a breakdown in 2017 of what events caused the largest amount of displacement. I don't want to spend a whole lot of time on that, but if you want to find out those kinds of details, go to the Internal Displacement Monitoring Center website, and they give you year after year in a lot of interactive detail. You can look at maps and what happened in each particular part of the earth. But all of this is hurricanes here. These are floods, monsoon floods, drought, typhoon, tropical storms, floods, tropical cyclones. These are all, the biggest ones were all climate-related disasters. This is from 2019, same kind of map. Again, if you look at Syria and the refugees from Syria, they're putting it due to conflict. And now it really has shifted to conflict, certainly. But I'll show you in a minute, underlyingly, the Syrian revolution was started because of climate change. And here, that kind of breakdown for 2019. In that case, in 2019, 33.4 million people were displaced, and of those, basically 25 million were displaced by disasters, and
So
24 million by climate disasters. Okay, yes, Bob?
It's mine. I'm sorry, I'm maybe hogging the questions. There seems to be, this displacement seems to be all water, almost all water related, the climate change displacement. I don't see anything related to like the temperature getting too high, making an unlivable situation, as may be the case in the future with like Phoenix.
That's a good point, and you're right, most of it is water, but not all of it. If you look down here, these are the wildfires part, and droughts also are temperature related because temperature affects the water availability. We'll talk about that in a minute. But yeah, most of it is water, but we're giving our climate and weather systems that much more energy. That means they can move more water or less water. and we expect more and more extremes. This just gives you across the years from 2009 to 2019, number of people displaced by conflict and natural disasters in each year. And for 2019, about 25 million people were displaced by natural disasters. And again, about 24 million of those were climate-related disasters. And again, if you go to their website, you can get a breakdown of exactly which disasters occurred where, how many people were affected, what was the cause of it. But if you look at this hazard type for all of these, and this is just a listing of countries alphabetically, reversed, so they started with Z and went towards A in this case. Hazard types: storm, storm, flood, 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 storm, 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 storm. So yes, other things like wildfires get in here, but the overwhelming thing is storms, floods, and droughts. Okay, so we can look at these different kinds of impacts in terms of rapid onset climate impacts like high temperatures, hurricanes and storms, floods and wildfires, or slower onset climate impacts like water stress, drought, crop failure, sea level rise, and those sorts of things. All of those things are involved, some of them more heavily than others. One thing to point out, as we're starting to look at the effect of extreme high temperatures, many different variables follow what is known as a bell curve, a normal distribution. So there's an average, and there tends to be, lower than the average distributed a certain way and higher than the average distributed a certain way, and you can see that here. But if you think about it, if this dotted line, dashed line, was the old average here, then the high temperature tails got into the hot extremes here. If we shift that whole bell curve normal distribution to hotter, what happens is basically we get that many more occurrences of those hot temperatures that we used to think were the top highest extremes, and we add on a whole new section of extremes outside of the range of what we've seen in the past. And that's really where people and species are affected in a more dramatic way by those extremes. So rise in deaths around the hottest days. So this is from United Kingdom. Data showed that in those times when they had heat wave warnings, people were dying as a result of those. We can look at the same thing for Las Vegas, heat-related mortality from 2006 to 2016. There's data from the Desert Research Institute. More people were dying, number of deaths as a result of heat across those years. Here's heat deaths in Arizona. And you can see that there's some variation, but that you can definitely see that there's been an increase in recent years.
Stefan, a question.
Yes.
This is from Zuba. I think this might have to do with the definition of natural disaster. Question was, it seems that there's much higher amount of natural disasters now than before human-caused high CO2 emissions. In geological time, is that a trend, also a trend? Like a high CO2, more natural disasters in geological time?
Well, good question, and that's a little bit harder to get at because we've got a good solid data on how the temperature has changed in the past. It's much harder to recreate what was the number of hurricanes 5,000 years ago. It's harder to track that, so I don't know the answer to your question. It's a good question, but certainly as the Earth's average temperature has changed, we know that higher temperatures relate to more storms, and so we can expect that back in the time when we had lower temperatures, we probably had fewer and weaker storms.
Isn't there a definition problem here too? I mean, if you say natural disaster, aren't we just referring to human disasters? I mean, if we go to geological time before humans and everybody living in Miami and on the coast in Vietnam, and we're not. We don't mean natural. We don't mean natural disasters in those geological times, do we? I mean,
sure we do. But the thing is, was it a disaster? If you didn't have huge cities sitting along a coastline, did the people at that time experience it as a disaster? No, they probably just moved inland a little bit. But of course, hurricanes would have affected them just as much. So sea level rise, hurricanes. There are different kinds of disasters and people experience them differently. Certainly, as we have more human infrastructure on the globe, we see the impact in a big way. So, yeah,
Maybe
I think you're right that it depends on how we define disaster and how we experience disaster. But
were
certainly,
these possibly natural disasters in terms of like extinction of species in the past?
right. And we know that, I'm not going to get into that today, but we know that all of these climate changes are exacerbating the global mass extinction that we're already going through. So relative to natural rates of extinction, what we're seeing now is orders of magnitude higher than the natural rate of extinction. And a large portion of that now is turning out to be climate change.
Is there any correlation between mass extinctions, let's say 1 million years ago or 100 million years ago, and CO2 and temperature?
Yes, in the hundreds of million of year category, we certainly had mass extinctions in the past. At the juncture, the Permian mass extinction was definitely caused by CO2. No question. It was massive amounts of volcanic activity that caused the Earth's average temperature to rise and the oceans to acidify in the same way that we're seeing now. And so there's no question that that particular mass extinction was caused by CO2. So we're kind of repeating geological history with what we're doing with human activities now.
Thank you.
Okay, so this is frequency of heat-associated deaths by year in Maricopa County, and we're seeing an increase there as temperatures continue to rise. This is getting into the newspapers now. Heat-related deaths soaring in Arizona and Nevada. This is from the New York Times. You can see in the graph down here that there's no question that heat-related deaths have been rising. In Arizona heat death summary, 75% folks who died from heat extremes were Arizona residents. 58% were over 55 years old and 79% were male. So this is affecting people somewhat differently depending on their demographics and age, but there's no question that heat-related deaths have been on the rise. Not just deaths, but also emergency room visits. Heat illness emergency room visits these look like slight increases, but an increase nonetheless, just from 2015 to 2018. And really, temperature has been high across that entire time. We know that tropical storms are rising in frequency, and I showed you all this last time. So I just want to go through it quickly. Hurricane Katrina, 2005, 2,000 killed, 400,000 displaced, costs were high. Hurricane Sandy, 2012, 750,000 people displaced. Hurricane Harvey, 2017, 30,000 people displaced. Maria in Puerto Rico displaced over 130,000. We still really don't have these numbers down solidly, but we know that over 3,000 people were killed in that particular storm. And other parts of the world are seeing this in even bigger ways. So I don't know if y'all remember Typhoon Haiyan back in 2013. It killed over 6,300 people in the Philippines and displaced over 4 million. So, we are seeing heavy impacts in the United States, but other parts of the world are seeing even heavier impacts already. This one didn't even get to our headlines here in this country. I don't know how many of y'all remember the floods in Peru of 2017. We were so busy with our own hurricanes, we didn't even pay attention to what was going on down there. Tornado count has been increasing as we expect. As we put more heat energy into our climate system, we expect more extremes, and we're seeing more frequent tornadoes, not only more frequent tornadoes, but also stronger tornadoes. I don't know if y'all remember Joplin, Missouri, back in 2011, but those were some of the largest swaths of destruction that we had ever seen in tornadoes. These are flooding projection maps of where people are at risk. And, this doesn't cover everything, of course, because we have had flooding in Arizona that doesn't show up at all here. We don't show up because we don't have the major rivers, but that doesn't mean that we're not affected by flooding at times too, because of extreme rainfall during our monsoon season and even at other times. Worldwide, many people are at risk from flooding. This is UNICEF, where they were looking at numbers of children at risk from flooding. And you can see that in a lot of parts of the world, children are at risk from flooding. They're saying more than 500 million children live in extremely high flood occurrence zones. And as we get more extreme storms more frequently, you can expect all of those kinds of risk categories to increase. There's just a picture from Bangladesh of some flooding events. And of course, these people are particularly vulnerable and their infrastructure perhaps is not quite as solid. And so they are heavily impacted by these kinds of events. And this is the picture I put up front. So some of these areas, they were flood prone naturally anyway. But as we intensify storms and increase the frequency of those storms, all of these people are being that much more affected and they just can't recover between storms the way they once could. Where are these people coming from? Where did that line start? It's hard to even tell. So drought is affecting people as well, not just floods and storms. I just want to make sure that we all understand that drought can occur even when we get slight increases in precipitation. And overall, if you look at this in the lower left, we've seen about a 5% increase in precipitation in the United States from 1895 through 2009. And if you think about it, if we're putting more heat energy into the atmosphere, well, warm air holds more water than cold air. So we do expect probably greater precipitation on average overall, but it's a slight increase, 5%. You can see here in the distribution map, some areas got drier, whereas other areas like southern Minnesota here got slightly wetter. And this is up through January 2007. So there had been an increase in precipitation in southern Minnesota. Yet in 2006, 2007, farmers in Minnesota were experiencing drought. So I just want to point out that even though you get a slight increase in precipitation, what else is going on here for the farmers is that because of the higher temperatures, so there's been an increase in precipitation in southern Minnesota here in this map, but there's also been an increase in temperature. And so even though you have a slight increase in precipitation, less of that water is available for plant growth simply because more of it evaporates because the temperatures are higher. Okay. So water availability for plant growth depends on not just precipitation, but also temperature and wind and some other factors. As a result of all these different, what we know is changing already and what we project to be changing in the future, the United Nations Environment Program in 2009 projected these kinds of changes in agricultural productivity across the globe. And they're expecting agricultural productivity in the United States to drop by 2080 and to increase in Canada. And certain parts of the United States are still fine according to that 2009 projection. Other parts of the world that are already in a tough spot because of other issues, we can just expect that all of those issues will be multiplied as climate change further affects agricultural productivity and things like that. We know planting zones are already shifting to the north. This is from the National Oceanic and Atmospheric Administration from 2012. And so farmers, in many ways, they can adjust to this fairly easily because they can just plant slightly different varieties of their crops or even shift to other crops as the planting zones move northward. For us in Flagstaff, this might be a good thing because we might be able to actually ripen tomatoes. But for natural systems, it's much harder because if you shift all the wildflowers to coming out a week or a month earlier because of temperature, and the insects aren't emerging until their normal time because they're adapted to come out with changes in day length, we can uncouple availability of pollinators and the availability of flowers. So natural systems are being affected in complex ways, and they don't have the option to just shift to a new type of crop next year the way farmers do. I think I mentioned this last time as well. We're already seeing it, on average, the Earth's average temperature has gone up by just over 1 centigrade degree already as a result of human-caused forcing. But it's not an even distribution across the surface of the Earth. So some of the northern latitudes have seen higher temperature rises over 3 degrees centigrade. And that particularly is the case during winter. And if you think about it, that makes sense because we're melting more snow. And so in those higher latitudes where normally they would be covered with reflective snow, they're no longer covered by reflective snow. And so much more of that incoming solar energy is being absorbed by the surface. And so you're seeing dramatic changes in temperature called polar amplification. As a result, places like Lacrete in northern Alberta, Canada, have been shifting from things like winter wheat to corn. They've seen a 3.6 degree Fahrenheit warmer, that's about a 2 degrees centigrade warmer conditions there already. And this is from the Wall Street Journal in November of 2018, pointed out that not only is the growing season, not only are the temperatures rising in Lacrete, Alberta, but the growing season is getting wider and wider. And so they're shifting to things like corn. The value of their corn producing land for Canada overall, what these bars represent is the percentage increase from the previous year in the value of that land. And for Alberta, they've seen steady increases in the value of their agricultural land. In the United States, not always. In some years in the United States and in some years in Iowa, there's actually been drops in the value of agricultural land. And that's going to be further affected as places like Canada turn to corn production and start to compete with our farmers here in the United States. And overall, Canadian corn production has been rising across this whole period from 1990 up through 2017. Temperature and precipitation in terms of crop growth aren't the only ways in which climate change is affecting farmers. In this case, what happened was we saw reductions in soybean productivity across the Midwest. And the reason was not because of lack of water or anything like that, but because there was too much water on the fields early in the season when farmers normally plant soybean. So they couldn't take their equipment out on the fields because the fields were just simply too wet. So farmers are affected by climate changes in a variety of different ways. And with expecting more extremes, it's hard to predict exactly when and how climate is going to affect a particular crop. Okay, I want to cover the Syrian conflict. And basically, Syria was already divided with many different sectarian divisions. It was Syria's drought, 2007 through 2010. And many of the farmers who were affected by that drought out here in these orange areas were Sunni Arab. 1.5 million Sunni Arab farmers could no longer feed their families. And in desperation, they fled to the cities. Now, the cities were already full of war refugees from Iraq. And so these additional people, the government could not support all these people flooding into the cities. They could not, or they did not. There was lack of trust because the ruling family was Alawite, which is a form of Shiite. And so there was not lack of trust between these Sunni farmers and the government. So basically, those folks who were not supported, they were in the cities. They started to protest. The government cracked down on the protests. And at that point, half of the military defected to form the Free Syrian Army, and that was the start of the revolution. So the steps of it went like this. This timeline, the cities in Syria were already flooded with Iraqi refugees. Now you had, because of the drought, and those droughts are exactly what the climate models for the Mediterranean region occur more intensely and more frequently. These additional refugees in the cities were not supported by the government, either because they couldn't or they didn't. These are the climate models for that region. They predict more intense and more frequent droughts for that whole region, including Syria. And these are drought severity maps from 2008. Okay, so across this time period from 1900 up through 2012, I believe it is in this case, you saw declining rainfall in the country of Syria. You saw rising temperatures, and again, less rainfall and rising temperatures makes that drought that much more intense because more of the water is lost through evaporation. The Palmer Drought Severity Index, which takes temperature and precipitation into account, was suggesting that drought conditions were getting pretty intense during that time. And across that entire time period, the Syrian population is growing, in part just because of natural human population growth, but also because you had all these war refugees from Iraq. Okay, so drought conditions were getting pretty extreme. And by pretty extreme, you remember the pictures I showed you from Minnesota drought. We're talking much more serious drought in Syria than what the farmers were facing in Minnesota. Under these conditions, people just could not support their families, and they fled to the city because they had no other options. This is a graph of Syrian wheat production from 1960 through to 2015, and you can see how the droughts show up in that wheat production. It greatly decreases the overall wheat productivity, but overall, if you look at this, wheat production increased across this entire time period with these droughts, with these drops in wheat production caused by the droughts. But even there, when wheat production dropped in 2007, 2008, it was really only taking it down to the level back from the 1980s. So why was the effect of this drought so extreme? And I think you probably are thinking of the answer. Okay, so here's wheat production across Iraq, Syria, Egypt, Iran, and Turkey. Many of these other countries were also experiencing these kinds of droughts. But what you've got to do is then realize that the population has been growing. So wheat production is dropping as a result of these droughts, and you really need to look at wheat production on a per capita basis. How much wheat production was there per person in these countries? And you can see in that context that these droughts were affecting the overall wheat availability per person in a pretty dramatic way. So all these people fled to the cities. They couldn't feed their families there either. They started to protest, saying, "Help us." The protests got more extreme. The Alawite government started becoming concerned, and they called out the military to shut down these protests, which is not ever going to be a solution. It started small, but as I said, half the military defected to form the Free Syrian Army, and that really was the start of the Syrian Revolution. So it was drought, exacerbating already difficult times with all the country being full of Iraqi war refugees, ultimately led to armed conflict. And this is 2014. You can see that the conflict didn't solve the food problem either, and things just got that much more extreme. And so at that point, you had millions of people fleeing. And this led to this is a Syrian refugee camp in 2015. So you can see that some of these people were internally displaced, but you can also see that this is not the kind of place you really want to live. And so people were not happy living in these refugee camps, and they fled further and left Syria. This is people showing up at borders and being turned away because people started shutting their borders when they saw just how many people were coming toward them. So disaster-induced displacement worldwide, this again is from the Internal Displacement Monitoring Center. But here, these are all climate-related displacements. And you can see that Syria doesn't even show up on this map. They considered all of these displacements here due to conflict. And certainly they were at that point, but all of that started with climate disaster. Okay, so Arizona's future. How does this relate to our situation in any way? Well, we're already seeing increasing temperatures. We're seeing more variable precipitation. We're seeing climate refugees already from Hurricane Katrina, Sandy, and Maria. We've got folks who fled to Flagstaff as a result of Hurricane Katrina, who are still members of our community today. And we can expect more as sea level rises. So I'm going to show you some projections on sea level rise and how that's going to affect internal displacement. And then our neighbors in Central America are already being affected by climate change. They're experiencing reduced water availability and reduced agricultural productivity as a result of it. And there's a net out migration that's been going on for years. Okay, so here are temperatures from Phoenix. And you can see that they've been getting more and more extreme from the 1930s up through the present. Here's another graph of the same thing. All the hottest years have been recent. And here, this is just what I was showing you earlier. As we shift the average, the extremes just get that much more extreme, and those extremes become more frequent. So it's not surprising that we're seeing greater numbers of deaths in places like Phoenix and Las Vegas. You know, this gives you an idea of extreme heat events 120 degrees, 124 degrees, 122 degrees. And that doesn't kill everybody. Some people have the resources and the wherewithal to cool their homes and stay home, but some people just don't have that ability economically or socially. And those are the folks that are affected in the biggest way. Currently, we have about 20 days a year in Phoenix that are above 110 degrees. By 2060, we can expect that to be 47 days a year. And by 2100, we can expect that to go up to over, 76 days a year being over 110 degrees. More projections for increased temperature. So we can expect these things to continue to intensify in the future. This is from the National Climate Assessment of 2018, and it pointed out that Phoenix, and I'd never heard this prior to the report coming out, Phoenix is recognizing this, and they're already putting in hydration stations and cooling refuges throughout the city because they want to avoid as many of these heat-related deaths as possible. And so they're giving people a way to survive the extreme heat events. So they're not talking about it in a big way, but they're doing it. And hopefully they're letting the communities know that they do have these hydration stations and cooling refuges available. Of course, those temperatures are affecting us in Flagstaff in northern Arizona in a big way because many people are now fleeing those extreme heat conditions. And those folks who can't afford it, they're buying second homes in places like Flagstaff, which changes our whole housing economy because you have all of these big expensive homes that are being built for folks to have second homes so they can come up during the summer and be in slightly cooler temperatures. We can expect that that kind of pressure will continue to intensify in future years and that we'll see more of that kind of thing. And I refer to those people as climate migrants. Those are folks who come temporarily to northern Arizona, but when during the cooler months, they go back to central Arizona. But ultimately, in the longer term, those climate migrants will also turn into climate refugees, people who move and stay. Temperatures for Flagstaff, at some point, Flagstaff also will become too warm and people will start fleeing here to move further north. This is a map 1991 to 2010, number of days a year above 100 degrees. You can see some areas are already, some parts of Arizona are already over 50 days. By 2060, we can expect many more areas to have that huge number of days above 100 degrees. And even in Flagstaff, we'll see more days above 100 degrees. We're already seeing it. And new homes are being built with air conditioning. Whereas if you go to homes built 20, 30 years ago, none of them had air conditioning. So people fleeing Hurricane Maria in Puerto Rico, these are the locations from which people filed relief applications to FEMA as a result of Hurricane Maria. And so you can see that some of those refugees from Puerto Rico ended up in Arizona. And this is not a solid measure, but it gives you some idea that yes, we already have climate refugees from Puerto Rico in Arizona, and many of them, because of the devastation of Hurricane Maria, are likely not to go back to Puerto Rico. We also know that sea level rise is already affecting real estate values in places like Miami. So in this particular article from the Wall Street Journal from April 21st, 2018, they were saying that rising sea level had already reduced real estate values along the coast by 7%, or 7% reduction in value of land. We can expect that to intensify as sea level continues to rise. This is a projection, and this is from a study, but it was put together by National Geographic, showing how many people are expected to leave these particular counties along the coastlines by the year 2100 if we continue with emissions business as usual. And you can see some plant like Miami-Dade County in Florida can expect almost 2 million people fleeing as a result of sea level rise. This is from that same study. Also includes projections on where are all of those people fleeing sea level rise going to go. And many of them are projected to flee to places like Arizona. And this gives you an idea of the projections from a study by Howard that was published in Nature Climate Change in 2017.
A question or a comment?
Yes, Bob.
This is from Bob Rothrock. He says, this is about back to northern Arizona. Our water supply in northern Arizona is groundwater. Warm temperatures result in less snow and more rain. Snow allows more water to percolate into the groundwater aquifer. More rain instead of snow will result in increased aquifer depletion than we already are experiencing due to drought and overpumping.
So, Bob, you're absolutely right. And yes, so if you look at the amount of groundwater in the 51 different water basins in the state of Arizona, many of those basins have a large amount of groundwater. But all of them, we are taking groundwater out faster than it's recharging. And by definition, that's just not sustainable. At some point, even if it's a long time in the future, we will run out. Oftentimes, as you get deeper and deeper into an aquifer of groundwater, you reach water that's salty or contaminated with metals or this or that. And so as we deplete those groundwater reservoirs, we can also expect that not only will we get less recharge because there's less snow and the runoff is faster, there's also, as we've been saying, more evaporative loss, which also affects the rate of recharge of those groundwater aquifers. Okay, human costs, and this is a study by Hsiang et al. In 2017. I'm showing the numbers for Yavapai County, but it's similar for Coconino County. We can expect to see a 10 to 15% increase in energy costs because of the need for cooling in places like Yavapai County. For Coconino County, a little bit less, somewhere between 0 and 5% increase in energy costs from cooling. And really, we see a little bit less in cost from heating during our winter months here in Coconino County. So in any case, there are folks who are projecting out what the energy shift in energy costs to people will be across counties if these kind of climate changes keep going in the direction that we expect. So these are projections from 2080 to 2099 relative to 1980 to 2010. Violent crime we can expect to see increases. So temperature is actually related to violent crime, and we can expect both for Yavapai and Coconino counties to see about a 3 to 4% increase in violent crime as a result of continuing rising in temperature. For property crime, 0 to 1% increase for both Yavapai County and Coconino County are expected. High-risk labor, those folks who work out on the power lines, who work out in the fields, who work on the highways, they're at higher risk of extreme temperatures and other weather-related issues, and we can expect to see a decrease in the availability of labor, people to work in those high-risk kinds of jobs. And these are the projections. So for Yavapai County, a 1.5 to 2% decrease. For Coconino County, a slightly lower decrease in the availability of those high-risk labor forces. Heat deaths, basically. And for Coconino County, many of our climate-related deaths have to do with freezing in the winter. In Yavapai County, it's probably more related to heat because I know Yavapai can get cold too, but don't have quite the same extreme cold conditions. So we can expect to see a 0 to 20% increase in mortality, climate-related mortality in Yavapai County, and somewhere between a 0 and 20% fewer climate-related mortalities in Coconino County. Again, that's because we'll see less of that extreme freezing temperature, which is really most of our climate-related deaths. Okay, I mentioned this last time as well. So we're seeing great changes in the rangeland productivity. Primarily, we're seeing an increase in fall wind, which reduces water availability for plant growth on the range during the fall, and ranchers and farmers are having to haul more hay and haul more water as a result of it. Many parts of Coconino County have seen as much, well, really even over 80% decrease in rangeland plant productivity. So the World Bank came out with a report called Groundswell in 2018, and they were looking at how climate change and other factors are going to change climate migrants between now and 2050. And they projected that we should see about 143 million additional climate migrants from climate change by 2050 in different parts of the world. So I want to take a quick look at some of that. So overall, they looked at Central and South America, referred to that as Latin America, the whole southern part of the continent of Africa, and India as well. And they expected to see greater increase in climate-related, they call them migrants, but I think, where are they going to go? They're going to be refugees. And it depends. The outcome depends on whether we just continue doing what we're doing with emission scenarios not reduced. If we use more inclusive development, where we bring people in lower socioeconomic categories along through job training and other kinds of shifts and keeping them from starving. And if we really reduce our emission scenarios, we can greatly lower those numbers of migrants that are anticipated. So they looked at all of these different factors in their study. It was very thorough. And for sub-Saharan Africa, they expect 86 million additional climate migrants by 2050 in the business as usual projections. For South Asia, 40 million, and for Latin America, including Central America, 17 million. These are the different emission scenarios that they were looking at, and the red line is the business as usual emission scenario, RCP 8.5. Whereas, if we really rein in our emissions, we could go as low as RCP 2.6, in which case we rein in a lot of those projections for additional climate refugees. We wouldn't go to zero because much of the climate change has already occurred. So those models for Central America, they project that there will be less water availability through much of Mexico and Nicaragua, El Salvador, Guatemala, Honduras. So for business as usual, that decrease in water availability is very extreme. For if we really rein into 2.6, the lowest emission scenario, then we'll still see reductions in water availability, but nothing quite as bad. And of course, less water available, less crop production. And so we expect to see drops in agricultural productivity in much of Central America, in the business as usual projections, and still some, but not nearly as extreme, in lower emission scenario projection. I'm going to skip some of this, but they looked at all the different socioeconomic models, and if we really bring people along by providing food, and training for new job skills, and all those different things, then that greatly moderates the number of people we can expect to become refugees. And basically they're saying, if we really pay attention to the United Nations Sustainable Development Goals by eliminating poverty, hunger, taking care of people's mental health, education and job training, gender equality, clean water and sanitation, affordable clean energy, healthy work, sustainable industry, equal human rights, sustainable cities and communities, responsible consumption, climate protection, terrestrial conservation and aquatic conservation, all of these different things. If we do them, then we can expect greatly fewer refugees to be fleeing these countries that are affected by climate change.
Stefan,
Yes, Bob.
I have a question. It's a comment too. We've learned about exponential growth with the current pandemic. Why can't governments consider exponential growth in human population? This is the root cause of climate change, since more people burn more fuels. But nobody seems to talk about it. Your last slide didn't talk about, the huge exponential growth in population.
It's such a sensitive topic, many people won't address it. But it is really the underlying cause of all of this. No question that even if all of us had small carbon footprints, you multiply that small carbon footprint by 7.7 billion, and you still have a large carbon footprint. So population is the underlying thing in all of this. Difficulty with population, the countries that have tried to greatly rein in population, like China. Mao Zedong was able to do that after he had tens of millions of people starving to death. And so then when he put in this limit on number of children, people could understand it because they had just gone through this mass starvation. People don't understand it here. And so education programs like this about climate change and the related population issues can get people's attention up to a certain point. But whether it really brings people to the point of having fewer children because of climate change projections, so far it doesn't seem to be happening.
Isn't it the easiest thing to change? I mean, we talk about all these things that need to change, and there's tens of trillions of dollars or hundreds of trillions of dollars that will be needed. And then you look at having one or two kids instead of 4 or 5 kids. It seems so much easier to make that change.
Yeah, I understand what you're saying, but at the same time, there's a huge time lag. So, even if we all started having fewer kids now, there'd be a long time lag before that had any effect on reducing our population size. But the more fundamental thing, I think, is that we are driven biologically, evolutionarily, to procreate, to have kids. And so it's a really difficult thing to reprogram within the human psyche to have fewer or no kids, because we were really programmed to have those kids. So there are a lot of issues and probably continue on. So again, depending on more inclusive development or lower emission scenarios, we can expect fewer climate migrants. But we're already seeing climate migrants. So the headlines often do not point out the connection between people showing up at the United States southern border and climate change. But occasionally they do, like in this, Central America's choice: pray for rain or migrate. And really, it's primarily 3 countries that have been affected by increased frequency and intensity of drought. And they are El Salvador, Guatemala, and Honduras. They're referred to as the Northern Triangle countries. They're all affected by intensifying drought. And what's happening when the farmers with non-irrigated cropland can no longer bring their crop to maturity because of drought or high temperature or both, where do they go? They can't feed their families, they flee to the cities. Well, the cities aren't necessarily in good shape either. So Tegucigalpa, Honduras, was affected by Hurricane Mitch in 1998. I don't know if any of you remember those headlines. It didn't really show up here in headlines in a big way. But so the cities are affected also, and many of the cities are also run by gangs of one sort or another. So people flee to the cities there, still can't make a living, can't support their families, and then they flee the country. So it's a complex set of situations. And it's not that they're all gang members coming to the United States. Really, they're the folks who didn't want to become gang members who are fleeing to the United States primarily. Okay, so these are apprehensions of people at the United States border coming from Guatemala, El Salvador, and Honduras, and the total from the Northern Triangle countries. And you can see that that has been increasing year after year as well, resulting in scenes like this. So if we don't understand that we are one of the main countries causing current climate change and don't take responsibility for it and just keep pushing these people away from our borders, it's not going to solve any of these situations. It's just going to build them into greater and greater crises. If you want to learn more about climate refugees, there are lots of different sources to go to. This is a good one from YouTube, Climate Refugees, a film put together about the many different ways in which climate is affecting people. Again, there's Old Man Rint to remind you. If you want some more reading sources, they're here. I know you all can't copy those down quickly enough, but again, if you put your contact information into the chat, I'll be able to share all of these resources, including the PowerPoint, with you. All that said, I don't want to just necessarily cut off here at the end. I'm willing to take more questions if Bob will translate them forward.
Emails additions in the last minute just from people adding their email addresses because they'd like your slides.
Oh, very good. Yes, and I'm eager to give them to you. So I'm glad to hear the interest. So thank you all very much for tuning in. Hit me if you have any more questions now.
With the higher temperature, Laura has a question. Stefan,
yes.
Would the higher temperature cause more violence?
Yes, it does. And I'm not enough of a sociologist, so I don't know how that relationship works. But in the graph that I showed you, they had that relationship. There's a very clear relationship between temperature and the amount of violent crime. So I guess people get angrier when it's hotter, perhaps. That's basically what the data are saying. I'm not sure what all the sociological reasons behind that are, but yeah, there's a clear relationship between those two things.
And that is it.
Okay. Well, thank you all again for coming in. Good to see you again, Bob. Bob and Bob.
See you. Thanks.
Thanks for joining in.